Alright, so this is where I was. So what happens, of course, is it's actually a very similar situation, as it says here, of when the star originally left the main sequence, but it's different in the following sense, right? There are actually two shells that are fusing, right? So the outer shell, of course, is still hydrogen turning into helium, and then there's an inner shell of helium burning. Remember, when we say burning, we really mean fusion. When the helium burning is going on, so that's the inner shell, and that's turning into carbon. Okay, but the carbon's not fusing. The stars like our sun don't quite have enough mass to convert carbon into. I mean, there's a little bit of that goes on, but you usually have to start with, you have stars more massive than the sun. So remember, this is we're looking at a star that is about the same mass as the sun. So we're in stage 11, and we're heading back to the giant stage. So this part right here going to stage 11, that's called the asymptotic branch, because what's going on, asymptotic giant branch, as it says, is remember, the helium flash occurred, so that's when helium begins to fuse into carbon. The star heats up and contracts. All right, so it's getting smaller, and then the helium into carbon. It will stay relatively stable for a while. It reaches stability, and that's that horizontal branch. And then from the horizontal branch, this isn't one particular. Would be a star exactly like the sun. It would head up this way. This can happen anywhere along the branch. So different mass stars. As long as it's about less than around 8 times the mass of the sun, somewhere they're going to where's my mouse? They're going to peel off in an asymptotic manner. And so what that means, let's go over what that means. That is, they will expand, right? So the star reaches this point of relative equilibrium, converting helium in the inner core into hydrogen, and of course the outer core, the outer shell, I should say. Sorry, not core. The outer shell of helium into carbon, and then the shell that's surrounding that of hydrogen into helium. It stabilizes, but then because you have this source of energy, and also there's of course the electron degeneracy pressure pushing back, as well as this source of energy. The star begins to in a nonlinear manner expand, right? So it begins to expand, but because it's expanding, it's cooling down, and so that part right there is called the asymptotic branch. But it becomes a red giant again, right? Remember, it was becoming a red giant over here from stage 8 to 9, and then there was a helium flash, and then we stabilized for a while anyway. Not very long, and not on like cosmic terms, not very long at all. And then it asymptotically becomes a red giant again. All right, so this is just showing an artist's rendition of what takes place with a low mass star like the sun. Eventually, so this second red giant phase will eventually, as we're going to see, let's go back. Oops, let's go back to this. These red giants will stay up here for a while, and will eventually end up way down here. and so notice what that means, right? So if you see something over here, that means high temperature, right? Because this is higher temperature on the x-axis, so going to the left, that's higher temperature. But notice the luminosity is incredibly low. So this region right here is what are called white dwarfs. So eventually, these red giants will eventually go down, 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 and become white dwarfs. And we're going to just talk about how that happens. Basically, the star loses part of itself. These outer shells get so large that basically gravity, the outer shell. So this is the outer shell of hydrogen and mixed with other things. It reaches beyond the escape velocity and just puffs out into the universe, or puffs out into the galaxy, really. But we're getting to that. All right. So right now we're just at the second red giant stage. All right. Let's see. The death of the low mass star. There's no more outward fusion pressure being generated in the core, which continues to contract. The outer layers become unstable, and eventually there's this ejection. So this is taking. They're showing what's happening to the radius. It gets bigger and bigger and bigger as you can see over, and this is over the course of less than 1 million years. So, and that is what we call the planetary nebula stage. All right. So the low mass star has grown. It has expanded so much that this shell of material, which is hydrogen, helium, some carbon, some oxygen, because that's what's been fusing. That has expanded so much that it begins to leave the star. It escapes, and they don't always. These planetary nebula are not always perfectly round the way this one appears. They have all sorts of bizarre shapes, as we're going to see, and sometimes that has to do with the fact that there's another companion star. In a binary system, one star dies, one star is still around, turning hydrogen into helium, and so this is not always very symmetric. And by the way, the name planetary nebula is actually not a good name for it. This has to do with astronomers about 200 to 150 years ago, looking out at the stars and then seeing this ring of material, and they thought that this was planets going around a star. It turns out that it's not. It's just the ashes of a star that is heading towards its final death in the form of a white dwarf. All right, so we'll get to that. So the star has two parts. It has an extremely dense carbon core, right? So that's the carbon core that's going on, and then there's this envelope. That's actually a better way to describe it. An envelope of material that is expanding outward, and it just keeps expanding, right? The material has reached the escape velocity because that was actually part of the star originally, right? That material came from the star and is so far from the star. Like for example, our sun, 10 billion years ago, will expand to when its first red giant stage will expand to around the orbit of the Earth, as a matter of fact, and then the second red giant phase, it just keeps expanding out beyond the orbit of Mars, and so that then that material just keeps expanding out into the galaxy, and that's if you had some observer looking towards our sun during that time, which is roughly 1 million years or so, the planetary nebula would be expanding away. So matter, and this is important. This when we actually are talking about, now that we're talking about stellar evolution, this planetary, the planetary nebula, it's not a planet, right, at all. It was just misnamed. Actually enriches the interstellar medium. That is the gas and dust that's out there in the galaxy is enhanced with heavier stuff than hydrogen and helium, right? Because this nebula contains things like carbon and oxygen and nitrogen. The more massive the star is, the more of that stuff, the more of the heavier elements, carbon, oxygen, nitrogen, and other stuff as well, right? Other things on the periodic table. And actually anything pretty much below iron. All right, so this is this is just kind of a snapshot of some different. So these are actual photographs, and taken in false color. They don't exactly look like this. It's just kind of enhance, what's going on with these planetary nebulas. So they're different shapes, and they have different names. I think is this one in the middle, I think, is called the Cat's Eye Nebula, and I forget what they're all called. I mean, there's different ones. All right. So anyhow, so during the planetary nebula stage, right? That is, stage 12 here. The stage 12 is the material is leaving the star and going out into the interstellar medium, and so the star is, getting smaller, physically getting smaller. What was once a star is and the only thing remaining is this really hot carbon core, and so materials leaves and leaves and leaves over time, and in fact, as the planetary nebula leaves the star, eventually you won't be able to see planetary nebula anymore. Because it's so far away from its original star, which is now just a core of carbon, that you don't even know necessarily where that stuff came from. Where the matter that you find out there between the stars came from, because it gets mixed up. It gets mixed up with all the other interstellar medium. But anyhow, the core. So now we concentrate on the core. It is very, very tiny and is really hot. Okay, but the heat is just thermal. Thermal. High temperature that is basically just cooling off, and these things take literally billions and billions of years. These white dwarfs will take billions of years to cool off. There really just hasn't really been enough time for them, in most of them, for these things to cool off completely and go from being white dwarfs to what we would call black dwarfs, where there's no emission at all, right? So the key thing is the white dwarfs are just cooling off, and we find these. We find these in our galaxy. We find these in other galaxies. All right. So this was actually one of the very first ones found. So here's Sirius, right? The brightest star in the northern hemisphere. It's actually the brightest star, the brightest apparent magnitude in the sky, and there's a little star near it called Sirius B, and it's very hard to see this star because the other star is just so much brighter, but we can see it. We can measure its mass. We can measure the energy output of it. I thought there was a little bit more about Sirius B. So it is a white dwarf. Um, and